Well, it's my pleasure to introduce Dr. Paul Petrus. Dr. Petrus is known as a Virginia Tech grad, PhD grad, 1997. He was one of my first students. He's now Vice President of Engineering at Ruckus Wireless, which is one of the trendsetters in the wireless industry. You can't go to one of the daily wireless blogs without hearing something about Ruckus in the news. Paul joined Ruckus in 2014 to start the new product line of CBRS. So it's kind of full circle in a way. Technology that was the baseline of that technology developed here at Virginia Tech. Prior to joining Ruckus, Paul was Senior Director of Technology at Qualcomm, where he led in the development of next generation 802.11ac chips. And he was the Engineering Internet of Things Initiative lead at Qualcomm, focusing on the low power technologies that went into the Xbox. And before that, his organization was a part of Authorized Communications. They were bought up by Qualcomm. Actually, Authorized is an output of a DARPA program you worked on. So you could see that, this is everybody is connected through some sort of degree. Another claim to fame for Dr. Petrus is that his dissertation was one of the most requested dissertations from the Virginia Tech Library for several years. And his PhD was in applying beamforming techniques to first generation cellular systems. So way ahead of his time, in fact, too ahead of his time. Paul, thank you for coming.
Thanks, Jeff. Should I stand there? Does it matter where I stand?
It doesn't matter.
It doesn't matter? Okay. I like to be close to people. Thank you. Thanks, Jeff. It's great to be back. I'm a Hokie. Everything started here for me. I got my gears. So I'm cool, excited. I came here because I brought my son, who just got admitted to engineering here, and we are in the final stages of making a decision. So it's awesome to be back. Great time. I had a wonderful time here at Tech, doing my master's and PhD here. And as Jeff said, a lot of the programs that we were working on in the 90s, it feels very old, by the way, when I say 90s. A lot of the DARPA programs that started here at Virginia Tech, NPRG was kind of founding a lot of these projects, and then it got on to do the multi-user MIMO stuff, MUD, multi-user detection, the interference cancellation, the antenna technologies, antenna arrays. All of them started. A lot of them we were working with some of the guys at Stanford as well. These programs were competing at that time, and great things came out, and it affected the industry. Today you look at the technologies, MIMO is like by default. You take that for granted. And at that time, those technologies were just getting evolved. So it was a fun time. I'm sure there's more pioneering work going on now. I'm going to talk about CBRS, Citizen Broadband Radio Service, which again was initiated here as part of the PCAS program. So if you look at a lot of the, before I jump into CBRS, I'm going to talk about Ruckus. Ruckus is been in the wireless industry for nearly 13, 14 years. It was a startup that came out of a little bit of a Stanford heritage in the Silicon Valley. We were primarily focusing on enterprise Wi-Fi. So if you look up here, I saw one of our competitors, that's the Aruba. We need to fix that. We'll change that to Ruckus. So if you look at the big three are Cisco, Aruba, and Ruckus. Ruckus is big in hospitality. So if you go to, we are about 60-70% of all the hotels. You go in and you get good Wi-Fi, it's usually Ruckus. 70% of the hotels throughout the world have a Ruckus in their Marriott, Hyatt, all these chains. Education, we're big in education as well. You know, you can see Stanford, USC, UPenn, Texas A&M. We cover all those universities.
We see Virginia Tech.
I know, it's sad. I mean, that hurts. Yeah, that hurts to see that. We'll get there. We'll fix it. I think we are working on the CBRS with Alan and Scott. We will do the Wi-Fi as well. We'll get there. We'll get a better wireless Wi-Fi here. And we also do a lot of big venues like stadiums, football stadiums. For example, the last World Cup, FIFA World Cup in Brazil, that the finals was fully Ruckus. It was all, there were like 70,000 customers. They were all sending pictures, and we have analytics of data that's get uploaded during the events and how it correlates to somebody scoring a goal or other events during the. So we have a lot of Sacramento Kings basketball stadium. Transportation is another area. We cover airports. San Jose International Airport is covered, and a few other worldwide as well. Service providers, retail. So basically, we have a lot of customers. We sell to a lot of enterprise customers. So we differentiate ourselves on performance. So if you look at any Wi-Fi, there's kind of the high grade, which is the enterprise. That's the high quality. You pay for that. So you don't go to Best Buy and buy a access point and put it in a VT campus. You don't do that, right? Because your performance will suck, and there's this level of expectations you all have. So that's where enterprise level Wi-Fi comes into picture, and for that you pay good dollars for that. And it comes with the cost. So retail we pay a little bit in the retail, but we don't pay a lot because it's a very cost-sensitive market. You know, enterprise is much more performance. They're willing to pay for the performance. So that's where Ruckus plays in terms of, and we have a lot of customers. In terms of what do we sell, these are access points, just like these ones. We have the Wi-Fi access points, and we are introducing the CBRS access points. CBRS just got launched yesterday. The product got launched, and we are the first in the market to launch the product. I'll talk more about CBRS. So in addition to these endpoints, the radio endpoints, these all connect back to switches. You know, they all have Ethernet cables that runs back, and they connect to switches. So we make the switches as well. So the switches are in your data center or your closet that's sitting in there for aggregating traffic and taking the traffic back to the backhaul of the buildings. And we also have management systems. Management systems are key to, especially in an enterprise, you need to manage these networks so that they don't have, if there's a performance issue, for example, this access point fails, you need to know why it failed. You need to know like how many users are on the system. How is it performing? How's the throughput of it? Uplink, downlink, and so on. Is it getting a higher level of interference? Because in the Wi-Fi, you can see this. We primarily on the 5 gigahertz band. There's a lot of channels in the 5 gigahertz band. You need to select the right channels and so on. So you can monitor all of them in these cloud-managed Wi-Fi portals that you can log in. And if you go up the stack, there's always the intelligence lies on the highest level. You know, the apps that are running on either in the cloud or in a mobile app, you want to securely log in. Users coming in, you don't want to be repeatedly having to push your password through. If you have Hotspot 2.0, you can log on very safely and securely. Network intelligence is another area where you can look at these networks and see how well they are performing and actually debug these networks as well. For example, if you have lower throughput or a lot of bit error rate on certain networks, you want to know a priori why it is degrading. Right? You don't want the IT. So these are all maintained by IT folks. The IT folks are not your wireless experts. And naturally, they are not necessarily they know IP. They can get switches. They can provide DHCP addresses, DNSS, and all this, but they're not definitely radio experts. That's where Ruckus comes in and provides this intelligence that you can actually look at these networks, and even if they don't understand exactly what channels they're using and what modulation they're using, at least they can debug it at a high level and provide the intelligence that they can fix some of the issues, or at least point back to Ruckus to saying, hey, there is an issue, these networks are going down, come and debug, and we use that. And location is another application they use. Where the users are, we want to know in terms of their mobility, where, if you see users are congregating in one particular location, for example, if you're in a mall and you're seeing users coming in through one of the entrance as opposed to the other entrance, they need to know, the mall owner needs to know that. They do a lot of business analytics based on that. So stop me if you have questions. It's a small crowd, so it can be interactive. So that's kind of the stack from hardware all the way up to the software. We provide end-to-end solution for Wi-Fi and for LTE. CBRS, I'm not sure everyone knows about CBRS, but so I will just not assume anything and start with the basics. CBRS, it's the new band that's getting opened up in the 3.5 gigahertz in the US, specifically in the US. This is some of the early work Jeff and his team have done. So if you look at traditionally cellular technology that you have your phones on, 2G, 3G, 4G, I'll talk about 5G later. 4G, these are all licensed band products. Right? Operators, AT&T, Verizon, Sprint, they own their spectrum, mostly below 2.7 gigahertz, anywhere between 600, 700 to 2.7. And you all know the propagation characteristics of those bands. 600, 700, beautiful. It can penetrate through walls and large area. 2.7, not so. So the real estate, 600, 700 megahertz is much more expensive. T-Mobile paid like billions of dollars to grab a 600, 700 megahertz spectrum. And if you look at the other extreme, use the Wi-Fi, Bluetooth, these are all unlicensed spectrum. Right? It's free. 2.4 gigahertz. There's some in the ISM band, 900 as well, but 5 gigahertz, predominantly 2.4 and 5 gigahertz have become, and that's propelled the entire industry. Now, FCC thought about this in the early 2000s, and that's how all this wireless technology is taken off, and you pay free. So here, they pay billions of dollars, so you are paying a monthly subscription for the service. When you have a Wi-Fi network, you don't pay anything. It's enterprises can put in or anybody can put in. CBRS is a mixed concept. It's a dynamically shared band. What does it mean? So if you look at it from 3.55 to 3.7 gigahertz, that's 150 megahertz of spectrum in the 3.5 gigahertz. It's 150 megahertz in LTE land, in the 3GPP land, it's like bonanza. It's like huge. Right? If you look at what they pay for billions of dollars, they get nationwide license for 5, 10 megahertz, 20 megahertz spectrum. AT&T is a T-Mobile. That's how prime real estate is at. And here you're talking 150 megahertz of spectrum. So, the early team, they looked at the spectrum. There's 150 megahertz spectrum, and you look at the entire country, it's not widely used. It's not very heavily used. It's sparsely used by these, what I call incumbents, the tier one. You see, those are US military radars. These are mainly like these Navy radars that comes in these big ships, military ships, and they use it for landing purposes, these flights to come and go. And they use the spectrum, and at any time they use only like, the signals that they transmit is only a few megahertz, so 2 to 3 megahertz, that is all. And it can be anywhere. Obviously the DoD doesn't tell us where they are transmitting, isn't it? They don't want you to know where the ships are. And the good thing is they don't land their aircrafts when they're close to the shores. So all operations are all away from the shores. Then there are other incumbents like the fixed satellite services. These are Earth satellites that are occupying about higher end of the 100 megahertz spectrum. And then there are wireless ISPs, call them WISPs. They provide fixed wireless services also. So there are a few incumbents in this frequency band, but they are sparsely used. If you look at the usage of it across the continental US, it's very sparse. So that's what initiated the whole idea is, hey, how do we effectively use this 150 megahertz of spectrum? So they came up with this concept of CBRS where if the incumbents are not using it in any given locale, why don't you use it? Use it for a good cause, for LTE as the seeding technology. And they tiered it as a two-tier mechanism in addition to the first tier is priority access license. Priority access licenses, you can actually, in the top 70 megahertz, you can actually get a license for a 10-year term on a county basis. So if you have a county here, you can actually go and buy that license. And the license ruling is one entity can get only up to like 40 megahertz. So they're forcing to have two entities sharing that in any given county level. So that's a good thing. But we expect these PAL licenses not to be as expensive. Because you're purchasing only at a county level, it doesn't get to be so expensive like billions of dollars. We expect it to be very, very low cost. And then there's a third tier, which is the entire 150 megahertz, is general authorized access. That means if nobody is using it, if there's no tier 1, there's no tier 2, you fall back to this GAA, which will be the case if you look here. There's nobody in this particular county. You will look at it. There are no incumbents there, and there's no PAL license yet. So the entire 150 megahertz can be used now. And in fact, we have put 5 access points in the engineering department, electrical in Durham Hall, and now we got an experimental license to use it. But eventually, in the next quarter or so, we can actually make it operational and use this as anywhere in the band, anywhere in the 150 megahertz of band. So that's the whole concept of dynamically you're sharing this. Right? If nobody is using it, you use it. Don't waste it. And also the PAL licenses, when they get the PAL licenses, if you don't use it, you share it. So you just cannot, unlike the license band today, if you get the license, you hog that area. You hog that, nobody else can use it because you paid all that money for it. But for the PAL licenses, if you don't use it, you have to share it. So it's a very open concept. It's a very innovative concept. I mean, US is leading its way. This is going to change the entire how spectrum is going to be looking for the rest of the decades. You can see. So that it also opens up a tremendous amount of opportunities for smaller networks to propel. Incumbents, as I talked about, the US military, the Navy, these are kind of the spin radars. You might have seen it in movies or video clips, these things that just spins around, those radars. They use that frequency, 3.5 gigahertz, and usually they have, I don't know if you've been on these things, these are amazing stuff. You go up here and you'll see these, one for landing strip and one for taking off, and these guys are constantly coordinating. It's just amazing, how precision they can just land and take off. And those signals are very, very small. There's only a few megahertz of occupancy there. The fixed satellite services are other incumbents, and also the wireless ISPs. Mostly the wireless ISPs have been the WiMAX deployments. When the WiMAX did in the 2000s, they're still operational WiMAX in that band as well, in the upper 50 megahertz of the band. And they all will be phased out in the next few years, and they all will go to CBRS. The tier 2 is the PAL layer. A little bit more into the PAL layers. The attributes are, if you look at the PAL layer, it scans this entire 100 megahertz, but at any region it's going to be assigned for a 70 megahertz portion. And it's got a space-time frequency constructs to it. Space is at the county level. It's going to be time. It's going to be a 10-year period. You get a license, you hold on for 10 years, and frequency is going to be 4 times 10 megahertz. That's each license. That's how it's going to be. And the preferred technology is LTE TDD, and LTE has been the dominant 3GPP technology for the past decade, and TDD is very natural to this band. 3.5 GHz is very natural TDD. As opposed to FDD, you need to allocate, downlink and separate uplink frequency. Here, it's the same. If you get a 10 megahertz spectrum, you can do LTE TDD, and you can do different TDD configurations. If you can do up and down ratios, you can do it very differently. And also, as CBRS is getting deployed, you will see there's tremendous noise about 5G in the industry. You're hearing every day, you're getting pounded and pounded. Just the volume is just I don't know if the signal to noise ratio is improving, but at least the S plus N is increasing tremendously over a period of time, and we expected that. I mean, when we were talking about CBRS is sort of a, LTE 3GPP technologies have a 10-year decade period. It's kind of 2G, 3G, 4G, 5G. Now it's coming to the end of the decade, and all the telecom engineers need a job for the next decade. So it's long. LTE used to call it long-term employment. Because it's like a decadal, you get into it, you can be employed for the next decade. So 5G is similarly facing. So every decade we find new ways to innovate. I'm just simplifying it, but there's more to it. But these use cases are coming together. Like traditionally it is only, if you look at it, it's your phone usage, isn't it? It started with a voice, and now we have data on it. Mobile is just one piece of the use case. And there's more to that. Now you've connected cars, you got connected cameras there. You got so many other applications that are getting built on top of it. And eventually, we as telecom providers, we just become providing pipes. And we started providing just as pipes, but we can do more than pipes. And we have to believe so that our long-term employment also goes. So applications that's why these kind of applications are building on top of these 4G and 5G as a transport pipe. And you will see more and more, especially in 5G, a lot of private applications that are shaping up. Then the third tier is the general access, authorized access, and this is really the last fallback where you can use the entire 150 megahertz, and again, LTE TDD is the primary technology for this entire band. So if you go back and look at the incumbents, this is a view of one of the incumbents. So if you look at the ships coming in, these are called protection zones. So the U.S. Department of Defense lined up, this is where the continental U.S., and we need to protect that. So if a ship is coming in here, you cannot use, if you're close to this in this protected area, you're not supposed to, you have to quit the channel. That is a construct. So they divide it into all these zones. So many DPAs, they call it dynamic protection zones. And to sense it, you need to have sensors deployed in each of the zones. Those are called environmental sensors. And typically there are going to be like hundreds of sensors on the East Coast and West Coast of the continental US. And every time there's a sensor detects it, then it talks to a central entity called a Spectrum Access Service, SAS. And the SAS will tell any of the access points which frequency to use. I'll go a little bit deeper into the system architecture of it. That's where things get really interesting. So at the onset, you want to avoid, whenever a ship comes in, whenever there's an event happening, you got to quit the channel. You got to get off, because they are the incumbents, they are the tier one. And it is based on the sensor network. So that's for the ships. Fixed satellite services, they are all over throughout the country. There's like a huge zone here in Texas. You have to avoid those as well. But again, in frequency-wise, they are only occupying like a 10 megahertz or 20 megahertz. narrow on that. So this is how the CBRS system looks like. So what you see here at the bottom, these are we call it the access points, or the terminology is CBSDs, Citizen Broadband Service Devices, like a Wi-Fi AP. Think of it as just like a Wi-Fi AP, except it's an LTE AP, works in this band. We call it CBSDs. And there are two types of classes of CBSDs. One is class A type, which is typically like an indoor. It'll just look like this one, which radiates less than 30 dBm. So it's a 1 watt or below, low power access points. And if you take it outdoor, then you got 47 dBm. That's up to 50 watts. These dBms are per 10 megahertz. So if you have multiple 10 megahertz, you get like 3 dB gains every time you double. So it's 30 dBm and 47 dBm. And they all talk to an entity called SAS, Spectrum Allocation Server. It's in the cloud. It's deployed in the cloud. It's basically, think of it as a database. It's a large database that knows all the space-time frequency information for every access point, every CBSD out there. And its primary job is it connects to the ESC, the environmental sensor, and make sure you protect the incumbents. And it also has a secondary job, is to make sure that these CBSDs can coexist. That's where coexistence comes into picture for these, because you are talking about these networks are not license band, so you can be anywhere if you're given an access to the top 100 megahertz, let's say there are like 20 access points in this building, and you're going to get the 100 megahertz, there's another 20 access points are going to sit there, and they're all going to interfere. And if you look at Wi-Fi, the Wi-Fi also does some kind of frequency allocation, but what it does is it does sensing, and it has a CSMA. So it has a carrier sense multiple access, where before every packet it senses a medium and then decides to transmit or not, which is not the most efficient if you look at it from a MAC efficiency perspective, it is not the most efficient. Every packet, it's like a group of people all talking together and they're kind of jamming each other. It's not the most efficient way. If you look at LTE TDD, it's a very time division duplexing. So it's very, I send a packet to you, next packet to you, line like that, and they go in round robin like that. So it's a very highly efficient technology. Right? The guard bands are the little bit inefficiency part. Otherwise, it's super efficiency. The efficiency is the order of 90% plus. You look at a classical Wi-Fi, the efficiency starts with like 67%. That means you're wasting 33% on just sensing and sending these signals to avoid. So Wi-Fi in general, that's why there's a lot of techniques that Wi-Fi is now borrowing from LTE LAN, from the 3GPP LAN to make it more efficient. But in general, inherently Wi-Fi was a very inefficient MAC technology. And LTE was much more rigid. But LTE is also much expensive. So you get what you pay for. LTE, a lot of research went into it by Qualcomm. So every time you have when you buy a phone, you look at, there's an LTE module in there, which costs about 10 times more than a Wi-Fi module. There's what is called Qualcomm tax you pay. Every time you buy a phone, there's a check that's getting returned to Qualcomm for all the IP that they developed over the years. So these two technologies are fundamentally very, very different. Different cost point, different performance. But LTE has been, over the last decade, it's been there for a long time, and it's gotten cheaper and cheaper over time. And CBRS adopting it is right at the point that it can be easily applied. So you'll see in 5G, 5G is going to start at this price. Qualcomm is spending tons of money into research, so they're going to charge you for that. So you'll pay for it, don't worry. And then it'll get cheaper over the decade, and then you'll see more and more devices getting using the 5G as well. So this one starts out, this borrowed the access technology from LTE LAN, 3GPP LAN, but you still need coordination. You cannot just deploy them randomly and expect it to perform. So you got these access points. That is the next set of challenges that this whole CBRS is going through. One is avoiding the incumbents. The next, how do you coexist together? So this is how the network topology looks like. It's a bit of an eye chart, but if you bear with me, I can just kind of quickly walk through. You have these access points which are talking to the switches. Here are all the devices. There are a lot of CBRS devices. It is defined in 3GPP as a band 48. It's for the entire 150 megahertz defined. So you need devices that can do band 48. So if you look at your phone, guess how many bands are there in your phone? There's a zillion bands. There's like 45 bands on your LTE modem here. So think about covering from 600 megahertz all the way up to, this is only like 2.6 gigahertz. So there's like, so all the tuning, everything that goes on. This is like, and you got Wi-Fi, LTE, NFC, all kinds of stuff. So you need to add one more, which is called band 48. And the devices are just getting out in the market. Pixel 3, Google just launched with Verizon, which has a band 48 now. There are cameras that are launching out with band 48, point of sales. A lot of devices are now for these applications. So, so if you look at, those are the devices. This is the access points out there being talked back through the switches, and everything else remains in the cloud. So the whole idea is, when you deploy these networks, it has to be very, very simple. When you plug in, you run an Ethernet cable, you just plug it in, and you have these LEDs. And a typical installer, when he comes in and he plugs it in, he just looks at those LEDs, and there are 5 LEDs, and they all turn green. He's a happy guy. He leaves them. That's it. That's the deployment. There's no more. He's not going around with his mobile app to measure what the RSRP is, what is the interference level, what is the blur level. He just, the guy doesn't know. He's not an RF engineer. So it's almost, when you take these technologies, all the complexities of the technologies, and just make it so dumb it down, a simple installer can just put it out, install those buildings, he walks through, and he gets out in like half a day. That's the whole mantra of simplifying this network. So there's tremendous amount of complexity built into it, but an end user need not know. And that's how we deploy it. That's kind of Ruckus' name to fame is, you make it simple. That's how you can deploy thousands and thousands of buildings. Otherwise, it takes a truck roll, somebody driving in. In one of our deployment, just to blow my own horn, I'll say, we had a competition. Our competitors in this space are Ericsson's and Nokia's. Those are big mammoths. They usually bring in a truck, and they do a forklift to bring in their equipments. And the guy came like a week before us, and he installed everything, and the system was working. And our guy just brought a backpack. He brought it in, he plugged it in, and it was working in like half an hour. And the guy was saying, when do I use the forklift? What forklift? You don't need a forklift for this. So because all the equipment that he brought, those are all installed in cloud now. We have EPCs in the cloud. We got SaaS management services. They all talk about to the cloud. You don't need physical equipment anymore. So the whole landscape of telecom is changing right before our eyes. There's the network technologies that are getting, the radio, the whole, before it used to be the radios and DSPs and FPGAs. They all are very central part of any communication system. That margin, the line is so blurred now. With 5G especially, all you need is you need an RF source. You cannot get rid of an RF source. That absolutely you need. Beyond that, all the processing is getting pushed back whether it is in your closet or data center or wherever it is. It's all in the cloud. So the whole architecture of wireless systems, how it's going to be deployed, is going to be very, very different in the next 5 to 10 years. So this is, in the passage, you can see this is kind of an evolution towards it. You have only a radio that sits out there, and then everything connects to a normal switch. You have a radio switch, and then All the other functions are in the cloud. A little bit going into protecting for those who are, I'm sure you're all graduate students, so you're theoretically inclined to calculate interference and so on. I put in a few slides which will tease your brain, and then you can start looking more deeper into it. So when you have these CBSDs, these are kind of access points. These look like towers, but these are access points. And if you're in a zone of a fixed satellite service, you will be allocated a transmit power. Ultimately, your transmit power is going to cause interference toward the incumbent. Right? And you can see two neighborhoods here. There's one protection area here. There's another protection area here. The SAS will calculate effectively the interference for each of the zones. If they're all sharing the same frequency, for example, that's with same frequency or adjacent frequency, there could be interference. So you calculate iteratively. You start with the CBSD, and let's say you set a transfer power to begin with, and you calculate interference using propagation models. So these SAS have all the terrain data, all the outdoor data. From the Google Maps and so on, you can have a tremendous amount of data now to calculate outdoor propagation, right? Which was not available when we were growing up. Now it's all available. I mean, it's amazing. Some of the Google tools you should look at, they have their own internal propagation tool, which can do X, Y, Z, and they also have these building data, building size and building material data. So they do ray tracing for any location. You just tell them where you put any transmitter power, any frequency, and it will spit out in about a few minutes. It spits out what the interference is going to be. It's just amazing. We did ray tracing for years. They all now come into this cloud-based computation power, and it's just incredibly amazing. I mean, people, if you love propagation, it's just amazing how the compute powers and what people can do now. So there's a lot of outdoor terrain data that's available. Indoor is a different construct. You don't know how many rooms are there, what materials are there. These all impact tremendously your calculation. But they use like a rule of thumb. If it's Virginia Tech, we know there's stones, the quarry stones, so you have certain dBs of attenuation of the. Normally they assume like a 15 dB of attenuation, but these are probably more like 50 dB of attenuation or so. So they use a lot of propagation models to start with to calculate the interference here, and then the algorithms go through iterative process of allocating transfer power to this CBSD, this CBSD, and go on, and then there's a certain interference margin you have, right? For a particular incumbent, these interference cannot exceed certain budget. Once it exceeds the budget, it just iteratively goes through the iterative process and make sure everybody is getting good transfer power to play with, and at the same time you don't exceed the overall budget. So that cycle is called IAP, iterative allocation process of transfer power for every region, and finally they get a transfer power, and then the SAS tells these CBSDs to transmit at that power or below the power. So you're not allowed to transmit beyond that particular power levels, and you have to. So the SAS. So if you look at the previous, so the SAS periodically talks to these access points. They call it what I call heartbeats. Every minute there's a heartbeat telling I am alive, here's the transfer power, and here's the frequency I'm using. So they're constantly talking to each other. If for some reason you lose the heartbeat, you need to terminate transmission. So the SAS is kind of the central brain for the whole system, and it allocates frequencies and so on. So that's the IAP cycle. They do it, it's agreed to do every day, this cycle. So for example, if you get let's say 40 megahertz of channel in this building and then 40 megahertz there, you may get a different 40 megahertz tomorrow if the IAP cycle goes through it. Little bit more into the coexistence piece. This is where a lot of the discussion now it's happening. It's kind of a dense slide, so bear with me. I'll just walk through. This is where there's a lot of questions on the CBRS when if it becomes really successful, how coexistence is going to be managed. Because you got all these disparate networks, and how do they going to coexist that they don't interfere with each other and bring it down? So the CBRS Alliance, which is an industry consortium that was formed years ago, has defined what is called groups. A coexistence group, CBRS Alliance have to adhere to certain rules. For example, the first one is if you belong to a group, you pick your LTE-TDD configuration. And as you know, LTE-TDD, it's got an uplink and downlink splits. You don't want to put two systems that are different splits next to each other. So if you have an LTE-TDD, one here and two here, and if a user is somewhere in the middle, they can interfere, uplink can collide with the downlink. You don't want that to happen. So that's the first level. So the SAS will tell, use TDD config 1 here, use the config 1 there as well. And then if there are others need config 2, then they can locate them together. There's kind of a lumping. But it's also, the lumping happens only those who are sharing the frequencies. If he is sharing a 100 megahertz or 40 megahertz of spectrum away from this 40 megahertz, you are allowed to use different configs. It is okay. But if you are colliding, if you are adjacent to each other in frequency, then you need to make sure that you don't choose different configurations. So the problem becomes very complicated because in LTE TDD, the uplink downlink ratios are different, so the usage is different. So I get different throughputs if I choose a different configuration. If I choose a config 1, I'll get 70 megabits in the downlink and 20 megahertz in the uplink. If I choose 2, it's 100 megabits and 10 megabits. So my usage could be very different because people could be uploading a lot of traffic, downloading. It all depends on the usage. So that's where the configuration becomes quite, there's a requirement for the customer that has to be enforced as well. And then once you select a TDD configuration, let's say we all agree, happy to be in the same configuration, you go in and then you look at now the channel. So you're kind of taking care of kind of the time scale of it. Right? Now you're going into frequency and space here. How do you manage the S and F domain here? So you can allocate, for example, if you're in this building, you can allocate 40 megahertz or 60 megahertz to all the CBSDs here. But anytime, any one of them will use only 10 megahertz. So in the LTE systems, they all the access points talk to each other, either through the radio or through a wired network. And they have what are called self-organizing networks that are constantly talking to each other and figuring out what transfer power to use, what channels to use, what PCIs to select, so that they don't interfere with each other. So it is a self-designed interference mitigation mechanism that's called self-organizing networks that is part of LTE for a long, long time. So that is how, if you give a 40 megahertz or 80 megahertz to this building, all these APs can talk to each other and they figure out a nice reuse pattern. You know, traditionally, if you go to an LTE deployment, an operator does, he's going to put a frequency here for this entire zone, a different frequency for that, and he will set up a reuse frequency, reuse of whatever. But you can't have an operator come into a building like this and plan out your frequency plan. It just becomes expensive. Then you have the truck roll, the guy staying here for 3 days charging VT a lot of money. You don't want that to do it. So that's why these LTE systems we have designed is they self-organize, they adjust themselves, they select the right PCIs, they select the cell IDs, they don't collide on frequencies all the way up. So that is part of this interference coordination group is that they are able to manage the interference among themselves. But these access points can talk to each other so they can manage. But the one on the other end there, in that building, they don't necessarily need to talk to. It could be think of it, this could be a Hyatt hotel, that is a Marriott hotel. They don't need to share any of the network behind it. So that's where the SAS comes in. The spectrum allocation server can look at, I'm going to give 40 megahertz here, 40 megahertz there, but they're going to be far apart. But I can reuse the same frequency when it is over there. And then if there is an event that's happening on a Lane Stadium, I can give them, they are quite isolated from the building at Durham Hall, things like that. So that level of coordination or interference coordination is going to be happening by giving them the SAS. The SAS is going to provide. So there's a lot of challenging coexistence that's still not all sorted out. This discussion has been going on for like nearly 2 years, with lots of PhDs scratching their heads in the CBRS Alliance, and they complicated way too much. I think in my mind, now we have to try. It's gone to the other extreme. Now we're trying to simplify that we can actually deploy the system. So there's still a lot of research over this. Tons of coloring schemes that are being proposed. But fundamentally, it's all based on propagation model. Right? So it need not be the best prediction of the channels that are given there, because it is based on a propagation model, and the propagation models are inaccurate, then you have inefficient use of it. So that's so how do we see this being used? This is kind of my last slide. So Ruckus see this as a huge disruption in the market, and this CBRS LTE can be deployed just like Wi-Fi. That's our mantra, is like deploy like Wi-Fi. Wi-Fi is very simplified deployment over the years, and we want to use it. So you can see, today we can see a lot of these embedded devices. In the next few years, you will start really seeing, devices like Amazon Echo and things like that, all going to see some form of CBRS. The cameras will start having these things. It's yet another, think of it as just yet another interface that's going to be there, like an Ethernet, Wi-Fi, Bluetooth, NFC, and now you will have CBRS as well. In building it solves the main problem. Is if you look here, if you want cellular coverage inside this building, you need to put, it's very hard to penetrate from outside. Right? Look at the stones. Right? And so you need to come in and deploy. Traditionally, they deploy what are called DAS systems, distributed antenna systems. Basically, you will see. I'm sure they have DAS systems. No DAS. Here.
Only in Lane Stadium and a few of the large residence halls.
There you go. That's a problem. That's a problem statement, right? Because you cannot. It's expensive. You have to afford to put those DAS systems. Lane Stadium, because they need it. They need to telecast it, so they need that. And there are customers coming in, students and users are paying for it, so you better provide some service. You need it. Everybody else, you're on your own. You have your Wi-Fi and that's it. If you don't get a phone call, good luck with that. Right? So we want to change that. That's where CBRS can come in to change that. Is now if you deploy these things just like Wi-Fi, you come in and you don't need the operator participation to it. You can set up a lot of private applications. Right? You can have cameras. You can have your own mission-critical applications on these. So a lot of private applications looking like push-to-talk phones, cameras, digital signages. They are offloading it from Wi-Fi. Wi-Fi is great. We sell Wi-Fi, so we love Wi-Fi. Wi-Fi is great for certain applications. Right? Wi-Fi is great bandwidth. It's not for efficiency. It's not for mobility. It's not for QoS, things like that. But LTE is greatly suited for those kind of applications, mobility and so on, and quality. If you make a voice call on a Wi-Fi, it's a hit or miss. Right? Voice over Wi-Fi can be, it depends on your Wi-Fi network, how good it is. But on LTE, it's always guaranteed. The LTE is ground up designed. So that's where the CBRS, we believe, is going to play a big role in terms of indoor cellular coverage that you can bring in, that you can actually start deploying for all these applications. We were actually talking to Scott and Alan with the team. There's an agriculture team. Scott calls it Internet of Cows. There's no access there. Even inside this way here, the operators are not allowed to come in and deploy anything here.
That was interesting. I found it because for the aesthetics of it, you don't want a tower sitting in the drill field, isn't it? That'll be the ugliest thing that everyone is going to look like. So they can only cover from outside in. So that means you have a nice cellular hole in there, isn't it? They have to kind of push it as well, and the buildings are at the mercy of the outside in coverage. So there's lots of opportunities, and people are imagining of lots of applications. Once you have these tools, you can imagine and come up with a lot of applications. So it's fantastic to see that. And smart cities and fixed wireless access is one of the things that's popping up, especially in the rural areas where fiber or there's no cable access to it. Rural areas, if you have a house in a farmhouse, you don't have access to it. Fixed wireless in CBRS, these deployments have already started now. And through this year, fixed wireless is getting to fruition. You will see nationwide deployment of outdoor CBRS happening towards the end of the year. The big cable operators like Charter, Comcast are all deploying outdoor networks. You might have seen they all becoming wireless operators now. And so they are starting to do CBRS is one of the ways to deploy that. So those are applications. I think hopefully that gives you a little bit of idea about the technology, the applications, and what the future looks for CBRS. And for the CBRS is not only 4G. This is a band for innovation. So 5G is going to be applicable as well. As 5G matures and the costs come down, then CBRS will. LTE is a great place to start because of the cost structures and so on. And it's a mature technology as well. And then 5G will find its place in CBRS as well. All right, thank you. And I will open up for any questions you may have. Yeah.
Just two quick questions. On your environmental sensor, assuming that the SAS is organized by the U.S. government and the tier 1 operators are the U.S. government, why don't they just coordinate directly to close the security hole of having an antenna since that they're present?
So I think if you look at TV white space. TV white space was a precursor in terms of the sensing technology, and the government was very much involved in it, in mandating that. That was in the 600 megahertz TV. TV spectrum is there, and there's all these air gaps in between. How do we effectively use that? That was the whole theme of TV white space. The white spaces inside. The government mandated was fully in control of those kind of SAS equivalent thing. And the entire ecosystem completely collapsed. There was no interop between it. There was no maintenance of it. The networks never flourished for various reasons. So in the CBRs, when it came out, they want to completely have the private sectors take control of it. They didn't want, we will spec you the characteristics, a little bit of the characteristics of the frequency and time, but they wanted the success of the whole ecosystem, and that's why and they want multiple competitors as well. So today, if you look at the SAS, there's like 6 or 7 SAS and ESC deployers, CommScope, Google, Federated Wireless, Sony. There's a bunch of people who have now taken stake in it because there's a business model to it. Anywhere there's money to be made, people participate in it, and there's an ecosystem. And they also interop with each other as well. So it's anytime you want an industry ecosystem to flourish, you want to give it to the industry because the industry does, at the end of the day, better. It's competition, isn't it? Everybody's driven by capitalism, making money, so it works out well. But in the meanwhile, it is a bit of a hassle to get those ESCs certified, ESCs meeting all the spec requirements, ESCs being deployed, all those things happen. But in the end, when we go through this hurdle, in the long term, it's a very survivable, the ecosystem survives. I don't know if it answered.
There's a very similar deployment model for UAVs being pushed by NASA. And so I think, as you stated with the SAS, they talk about having like an industry run it, and so you have like a Google that would say, I'll coordinate all UAVs in the area, but they still talk back to the FAA to close down airspace.
Yeah. Yeah, okay. So there's a slightly different model. It looks like the FAA has that database. Here, there's no database, centralized database for ships coming in and out. They all kind of do their own random thing. And then the fixed wireless, there's a good database. And you know, because they're not moving anywhere. So that's a good database. You can have it. But it's not a centralized government-owned database as well. So there's a multiple, 2 or 3 databases that are kind of, one is moving around, one is fixed, and so on. So they're just like, okay, let's just put them all into one combined database, give that entity that authority to control it. And so far, they've done pretty well. Over the last 3 years, they have really, because this is a very heavy system. If you look at it, the SAS coordination and ESC, it's a pretty heavy system, but it's a good price to pay if everything comes out. And the ecosystem has really come out well. And the ESCs are deployed through CommScope and Google share an ESC federated as well. And federated has already deployed all of the ESCs, so they are in operational now. So by the second half of the year, most of the ESC networks will be operational. Yeah.
Do you see CBRS being extended into that management approach being extended into other bands?
Good question. In the US, there are a few other bands that are opening up, 3.7 to 4.2, that's one band. Potentially sharing can happen. And even below it, I think the FCC is looking for the success in this 150 megahertz. And it's like if you raise a kid, you know, like first give him a $20 and see how well he spends that, then they'll give you another 20. And it's like that approach. So they're like, okay, we gave you 150. Let's see how good you make use of it. And they are, we're making a lot of progress. I think FCC is happy. I hope they're happy because there's tremendous, there's hundreds and hundreds of millions of dollars of investment has gone in, and it's coming to, and we are pushing. FCC, I heard they're super happy with the success so far, and they see real deployments. That's what they want to. And 3.4 to 3.5, they're also planning to open up. And the rest of the world is looking at it with awe, how this thing is going to work out, because everybody have this 3.5 gigahertz spectrum around the world. So 3.5 gigahertz system used to be called the garbage spectrum because its propagation characteristics were not that great as the 2.4 people thought, unless you until you run out of spectrum. It's all, you run out now, people are talking about millimeter wave, whose radius coverage is like this much, and still everybody's like going gung-ho. It's funny how things change. So 3.5 gigahertz, now it's seen the mid-band. Now it has an official definition of mid-band. It's seen as a prime real estate now. Throughout the world, everybody is going on 3.5 gigahertz now. China's doing 5G, all 3.5 gigahertz. US is a little bit stuck in the 3.5 gigahertz CBRS primarily, but not 5G. 5G is a millimeter wave. So there are other regions, other countries that are looking at sort of shared concept, not in the way CBRS is constructed.
Europe was pushing some alternative
Yes.
to this SAS. I certainly can't think of the name of it. But
So
LAA, okay.
yeah. So so Germany and Netherlands are now opening up. Europe also has a lot of different bodies, and they don't all agree together on the same playing rules. But Germany just announced its rulings for local licensing. So that means in the 3.5 gigahertz, I can actually I can pay like, in Netherlands, you pay like $100 and you can get for your building license for a long time. So it's in the 3.5 gigahertz band. So it's more a static database. You can see it's not a dynamic, it's a static sharing. As long as nobody else is using, I can just get this thing, and the other guy can get, for his $100, he can get spectrum. So this concept, CBRS is kind of the lighthouse for the rest of the world. If you see this success, it's going to percolate through all the other, wherever this band is going to be. It'll be slightly, the concept is going to be a little different, but sharing is good. Sharing is the future. Sharing is caring, isn't it? So you gotta do that.
LAA is 2 tiers, right?
So LA is, they have, do they call it LA?
License assisted access.
That's the 5 gigahertz.
Different.
It's a 2-tier kind of incumbents, which are primarily mobile operators, and then these local licensees. So still the local operators are the ones who own that, and the local license you get from the operators. So it is still TBD. You know how operators behave, and so good luck. You know.
But I mean, a few years ago, they would have said, "Oh, this three-tiered thing that the U.S. is trying to do is too complicated."
It's too exactly. That's exactly what they were saying. They were poo-pooing the whole thing, and now they're seeing the success of it, and they say, "Oh, okay, maybe sharing is not that bad." But you still the tier 1 is an operator, so you are at the mercy of an operator to give you the license, which is there's no operator mercy here. I think that's what the FCC had the oversight to completely decouple that, because the big boys play big game. Right? The little guys need a little playgrounds too. So and that's how. Yeah.
But you see that in politics of other countries as well.
Yeah.
I was in Taiwan doing a talk, and they were trying to decide LAA or CBRS. They were under tremendous political pressure from carriers
Yeah.
not to do
Yes.
CBRS.
Exactly. Yeah. Even in the U.S., as the PAL licensing was settled, there was tremendous pressure to increase, because originally we wanted to be at the census tract level, which is like a very small geographical area I can get licensed. Now it's a county level. County is pretty big. If you're going to get a license, a county is like, I don't know, it's like an entire Blacksburg, or it's large. All I need is just for this building. I don't need to get a license for that. So operators played a role to expand the space dimension of it, which makes it harder for smaller guys to play in that.
Can they allow for sub-licensing?
Yeah, good point. So you can buy a large license, kind of county level, and you can do sub-licensing, and that system is not set up, but that's the next idea behind it, is to sub-license it and sell it to, Virginia Tech can have it, Hyatt Place can have it, and so on. Yeah.
So is that a good business model?
It's a good business model, I think. But again, you need to manage interference. Again, you have to provide certain. It's all about ultimately you have to provide some level of. If you're going to charge somebody, to make it a good business model, you're going to charge somebody. If you're going to charge somebody, you got to have some good SLAs and maintenance and agreement. So you need to work through all of that to make sure that you can actually have a successful business model.
So maybe take one more question. If there's another question.
Yes.
So you said the transparent powers on the CBRS AP is inside that says control that refers to a common user below some threshold.
Mm-hmm.
And I suppose you can calculate the path loss based on Google Map, but how do we incorporate fadings? Because
there's always a fading margin,
yes,
that's associated with it, 10 dB or whatever you come up with. These are standardized models that have been, as part of WIN forum, there's a forum that decided it. They have a very standard propagation path loss model that you can use a very standard propagation model. That's kind of the basic model, and then you can use a ray tracing based model as well. So kind of short-term fading, they just take a fading margin. Large-scale fading, they do either through some propagation path loss model or ray tracing, and then add some margin for the dynamic part of it.
you mean for small-scale fading, just maybe take the average?
No, they just do a margin, like it's a fading margin. Just put like 5 dB, 10 dB. You become conservative. You're probably going to be conservative at that point, but it's statistical. Yeah. Mm. Cool. All right.
Well, thank you.
Thank you, guys. Thanks.